Okay, so I'll try and talk through everything that's on the slides. If I miss stuff and you'd like some clarification, just stick your hand up and ask a question. As it's the last session, I'm going to try and get through this relatively quickly, so just ask questions if I'm going too fast or there's something you want to know about. So this presentation's entitled Practical Performance, and it's not a deep dive into how to tune the operating system, how to enable large pages, whether you want to adjust run queues and use RAM disks for fast I/O. It's not an in-depth guide to tuning garbage collection or anything like that. What it is a high-level methodology and process of how to go through the standard performance analysis and tuning process for an entire deployment. And it teaches kind of like the 70-30, 80-20 rule. It will highlight the major things that you want to look for, but it doesn't go into real detail. But if you've got questions about specific things, I'm quite happy to have a conversation about that afterwards. So, yeah, the presentation's practical performance. On the first slide of every IBM presentation is one of these. It's a legal disclaimer. If you can't see it at the back, you're lucky. And what's even better than that is they've done it in block capitals to make it harder to read because legal statements are a little bit too easy. So if we ignore that, okay, me. So I work for IBM in the Java Technology Centre based in the UK in a village called Hursley. I've been working as part of the Java Technology Centre for 12 years and 11 months and 2.5 weeks or something. I get my 13th birthday on October 20th. And in those almost 13 years, I've spent my time working on customer engagements, doing customer support and consultancy. And then I've moved on to that to doing usability, so monitoring, diagnostic tools, etc. And I'm now doing the deployment of Java into the cloud. So what's in these slides is kind of a high-level summary of the sort of thing that I used to do with customers for years. My contact information is at the bottom, so it's an IBM email address. I'm on LinkedIn as Chris Bailey IBM, so it's easy to find. And I'm on slideshare.net, which is where these slides will go. Everything that I presented at Java 1 this week is going to be on SlideShare for you to download if you want them. So the goals of the talk, as I said, is to introduce a general methodology to performance analysis and trying to identify performance bottlenecks in your system. So it's the high-level process rather than the detail of how to analyze and tune specific areas. What it will do, though, is cover some common performance bottlenecks, things which will have a noticeable impact to your system. And we'll go through a process of looking at a sample application and correcting some things and seeing what the improvement is. And that'll give you a guideline of the sorts of improvements you can actually make to your own system. So in order to do that, we'll start off with the approaches to performance. We'll look at layers of the application, so operating system, JVM, application, external resources, and so on. And as I said, we'll do some examples of how to look at each of those areas to try and resolve performance issues. So really there's two major approaches to looking at performance. The first of them is kind of outside in. And this tends to work better when you've got an identified performance problem. So you've got a user that says, if I do this action, performance sucks. If you've got that, you already have your start point. You have a user metric that they care about. And if you've got that, it makes sense to take an outside-in approach, right? So you've got the performance maybe at the HTTP server, and you can track that transaction all the way through the system. So from the HTTP server through to a servlet, through to an EJB invoke, through to JDBC drivers, through to the database, and then you can track it all the way back again. So you can put timings in there to find out which of these steps is causing your performance problem. But that's a very specific approach. You need to know that there's a problem there before you can start. The other side to this is the layered approach, which is probably more appropriate if you're starting off just doing general performance improvements. So I want to health check my system, and I want to see if there's any glaring bottlenecks that I can start working on. So when you're taking the layered approach, obviously there's two ways you can approach layers. You can either start at the top and work down, or you can work at the bottom and work up. Now, I always advocate starting at the bottom and working up. So looking at the machine first, then the operating system, then the Java runtime, then your application, and then maybe external things that your application accesses. And the reason for that is, in all honesty, at the machine level, there's not much for you to look at. So there's only a couple of things you need to do to check whether it's right or wrong. And correcting it doesn't take too much effort. And it gets harder to analyze and harder to diagnose and harder to change as you go up the stack. So the easy wins are at the bottom. And the hard work, which may involve changing your application, changing architecture, changing your code, getting developers working on this, is at the top of the stack in your application. So I always start at the bottom where I believe it's easiest to identify problems and make changes. So before you start anything, you first of all need a performance baseline. You need to do a performance test to find out where you are at the moment. And because we're going to be doing performance improvements, then we want to check whether it's actually improved it. You need a repeatable test. You need something that you can run again and again and again. And it needs to be representative of the workload you're actually going to be doing in production. Right? These are obvious things, but it's actually quite hard to get a representative test. You can use things like Apache JMeter, Load Runner, Rational Performance Tester. There's a whole load of tools which will record user actions and run that multi-threaded against an application. But if you only hit 2 or 3 code paths, you're going to end up with a test that's not particularly representative. Now, there was a pitch on Monday, I think it was, by a guy called Rene, who works for a futures exchange in Chicago, CME. And the approach that they take to this is actually quite elegant. What they do is they actually record every single transaction that comes into their system throughout the entire week. And they use that to identify their 6 minutes of busiest workload, record it, and they run that through the system on the weekends. So they have a system that's only up Monday to Friday. They therefore have Saturday and Sunday in order to run performance tests. So they use exact workloads from during the week at the peak of what they need to be able to react to, and that's their workload that they can run repeatedly. So you need to find a way of having something that's representative and repeatable. You need to be able to run it several times. So once you've got that, and you've got the ability to run it several times, you need to make sure that the system that you're running your test on is consistent. And there's 2 ways that you really want to be consistent. The first is it needs to be representative of production. Right? Having a test system that's got different hardware, has got different memory, has got different levels of network associated with it, is going to have a big difference to the way the test is run, and it can well identify different bottlenecks. Right? If you run on a test system where you don't have the same level of network capacity, your application is going to run slow because of your network connections, and you won't necessarily identify the bottlenecks in your application that you'll find if you're running it in production. So you do really need, ideally, the same level of hardware. And the other side of ensuring consistency isn't just your test system to where the performance matters, it's in the state of the system when you're running the tests. So there's actually some really interesting stuff that happens at the hardware level. So when you run an application, bits of your application gets loaded into memory, and it gets cached. And whether you've got useful data in cache or irrelevant data in cache is actually going to affect your performance test. So ideally, you actually want to clean out the entire system and start from exactly the same baseline when you run each of the tests. Now that's actually quite hard to do. And one way of doing this is to run your test several times before you start measuring. And that's primed it to a certain situation. And if you can do that repeatedly, then you kind of avoid some of these hardware issues that can arise. So those are the kinds of things that you want to do. In all honesty, the important thing is have a baseline, have it repeatable so that you can then test after you've made changes that those changes made a performance improvement. And as far as possible, make it representative of what your application actually does in production. So what I've done is I've taken a simple application. And that simple application is the WebSphere application server running plants by WebSphere, which is a sample that gets shipped with it. And in order to create a performance test, ideally I would have had production data, but it's just a sample. So I took something like JMeter. ran its proxy server that lets me click around on some windows and save that as activity, and I ran that with 10 concurrent users from a remote system. So that's my consistent performance test. I can run that several times. And the tooling that I was using gives me a breakdown of the average responsiveness for each of the pages and each of the actions that's done by the load generation tool. So this gives me a profile of the responsiveness of different bits of my application. So this is my baseline. This is where I'm working from and I'm trying to improve on as I go through the process. So I've got my baseline. Now, I said to do a generalized approach to looking at performance, I would take a layered approach and I would start at the infrastructure, at the bottom, and then work my way up. And when it comes to looking at the infrastructure, largely there's two things you need to look at. And that's going to be CPU, and it's going to be physical memory availability. So that's what you've got at the infrastructure level with your operating system and the machine hardware. If you move up one more level, at the Java runtime, in all honesty, there's not much you can influence other than garbage collection. So really, garbage collection is the only thing worth looking at the Java runtime layer. Then above that, at the Java application, you've got all of your Java application code, and that's going to have potential issues around memory, CPU usage, synchronization, so synchronized blocks and contention locks, and I/O. So those are the four resources that could be applicable at each level, but really they're only applicable at the application level. At infrastructure, it's CPU and RAM. At the Java runtime, it's really just CPU and memory, which is both garbage collection. And then at your application, there's scope for all of them. So at the infrastructure level, if you don't have enough memory, then you're going to page. Right? You start backing bits of your application's memory with disk. And spinning disk is, well, it's slow. And certainly an order of magnitude slower than having RAM in which to store your application and access memory. So memory is a big issue. The next one is CPU. So if you don't have enough CPU for the amount of load that's coming into the system, then you can only scale so far. You'll reach a maximum level of responsiveness and stop. And in fact, if you have too much workload, you end up contending on the CPU that's there and your performance drops off. So you actually lose performance if you don't have enough CPU. It doesn't just stop getting better, it actually starts to get worse after that. So memory and CPU are pretty big. I/O is another one, but it tends to be a little bit harder to work out what's going on there, and it's not something I'm actually going to cover here. So memory usage. So RAM on the system is used for a few things. So it's used for your application. So the Java heap, the JVM, the operating system is all backed by physical memory. And it's also used to cache files. So if your application reads or writes to and from file, what the operating system will do is it will try and hold those files in memory so that the access is quicker. Right? It doesn't go and writes that file change directly to the disk because that's slow. It writes it to memory, and then that memory will slowly write it back out to disk afterwards. So it does make it there eventually, but it's not a blocking event. So your RAM's actually going to be used for two things. It's not just used to back all of the applications, it's used for files as well. And if you run out of physical memory, if you don't have enough, the first thing the operating system will do is take it away from file caching, so your I/O gets slower. And then it takes it away from the application and has to back your application with spinning disk, which is slow. So accesses to bits of the Java heap slow down. And that's one of the reasons why most people are aware that paging is bad for a Java application. Right? It's mentioned a lot. And the reason for this is really garbage collection. So operating systems design paging that the bits of memory which you're not using are the ones that they'll write out to disk, and that get backed by spinning disk. Now, that works well because we've paged out the stuff that you don't actually need, that you're never going to access. So the idea is, put on disk, give the performance problem to the things that we're not going to worry about. Then the unique thing about Java is garbage collection kicks in. And in order for garbage collection to work out which bits of the application you're using, it has to also identify which bits of the application you're not using. And those are going to be the things that are paged out to disk. So it walks through every single bit of memory, including the stuff that's been paged down. So whereas a normal application wouldn't touch it at all, garbage collection does. So that's why paging's particularly bad for Java and much worse than it would be for other application types. So paging is a particularly bad thing. So next is CPU usage. If you don't have enough CPU, as I said, you'll reach the limit of how far your application will scale, and then once you've gone past it and your CPU is running at 100%, you actually start to slowly degrade performance because your different bits of the application are competing for the CPU. So that's what happens if you don't have enough overall CPU. The other type of problem that can occur is if you've got other processes on the same machine which spike their CPU usage and suddenly take all of it. And a good example of this is databases doing a backup job at, say, 1 o'clock in the morning. When the database is backing up, the rest of the applications on the box run slowly. So if you get a very specific performance impact at a given point in time, there's a good chance something else in the box has just stolen all of the CPU. So how to check for this? Well, you're looking at OS level resource contention, and that means it changes by OS. The way to do it on Windows is listed there. So on Windows, there's a tool called perfmon. Does anybody know about perfmon? Oh, that's pretty good. A few of you do. So it's built into the operating system, and Windows effectively puts counters in everything that it does. And perfmon lets you access those counters and graph them. So if you care about paging, inside perfmon, there's a pull-down menu for process counters, and under the process counters, there's page faults. So that basically says, tell me about the page faults that are happening on the system. You can do the same thing for file cache to find out whether it's taken all the memory away from the file cache, so you don't have any file caching done by the OS anymore. And that's just a different counter. You go to memory, and you go to system cache resident bytes. So that lets you look at paging. There's similar counters for CPU usage. So you can find out about the CPU usage of your application or of individual threads inside an application. And it gives you similar counters for I/O. Now, if you wanted to do this sort of thing on Linux, so for most of CPU and memory, you'd be using top, but you can also use PS. On AIX, you'd be using top AS, and you'd be using VMstat to look for paging. So the tools change per operating system. But they are all available. Now, if we go in and look at my test case running on Windows, this is what perfmon shows me for paging. So those spikes of activity is paging happening on the system. And there's a pretty good chance that those spikes of paging activity happen at the same time as garbage collection. Because as I said, garbage collection pages in all of my memory. It touches every single bit of memory to work out what's live and what's dead. So if paging's going to happen, it's going to happen during GC. So those spikes in paging happening on my system happen at the same time as garbage collection. So that says to me that I want to fix paging, because it's probably having an effect on my application. Now, the way you fix paging is fairly simple. You give your system more memory. There's not much more you can do than that. So if you're in a virtualized environment, you can assign more real memory to it. You can stick it on a box on its own if there's other things there which are using memory. But effectively, you've got to give it more memory. And it's the same with CPU or I/O. If that's your bottleneck, really what you have to do is give the system more of it. And that's why, in some ways, it's a simple thing to fix, because there's nothing complicated here. In a lot of ways, it's a difficult thing to fix, because if you need more RAM, it's a good chance you have to order it through procurement if you work for a large company, and that's like 3 or 4 months. So this is where we started off, right? We started off with our baseline, and I can run my baseline, and I realized I've got paging, so luckily I'm on a virtualized environment. I can just assign more RAM to this partition and take it away from another one. So the effect of doing that is this. I have a very slight increase or in my throughput performance for each page, which is a very slight decrease in the responsiveness of each of the pages. So my performance has got better. That red line is slightly lower than each of the others. Now, the performance is only very slightly better, and that's maybe not what you expected. So here's the breakdown per page, Right, a couple of pages actually have a noticeable percentage improvement, but the ones where there's a big percentage improvement are the ones that didn't take a lot of time in the first place. The overall improvement is actually only about 4%. So my entire application, as a result of removing paging, is now actually only running about 4% faster. Now, as I said, paging tends to happen during garbage collection. So do we only have a 4% change in garbage collection? So what's on the screen here at the moment is a graph of my garbage collection pause times. So this is how long each of the garbage collection cycles took. And the longest took about 1.1 seconds. In the table below, there's a full breakdown, a statistical analysis of it. And it says that the overall GC overhead, so that's the amount of time spent doing garbage collection versus running the application, in this case was about 8%. So about 8% of my time is spent in GC, and I have pause times of up to 1.2 seconds. Now, if I look at the same picture after fixing my paging problem, I now have a longest pause time of more like 0.65 seconds. So my pause times have cut in half. And my total amount of time in GC, my GC overhead, has gone down by about 2%. So I'm spending less time in GC, but the biggest change is my pause times have now dropped significantly because I'm not having to page in and page out when I'm doing garbage collection. So possibly the surprising thing there is that during the normal runtime of my application, paging hasn't particularly affected it. But what it has done is cause these 1.2 second delays in garbage collection. And if you've got responsiveness SLAs, service level agreements on your transactions, then that's where it's going to kill you. It's going to be the outliers where you have long transactions. The application itself isn't too affected because all of the bits of the application which you're running have been paged in, and it's the stuff that you're not using that's been paged out. Now, I will also admit that the paging happening here isn't significant. Right? If paging does become significant, then overall throughput does degrade as well. But for small levels of paging, it actually only hits GC. So here's the summary of those, the effect on GC pause times. The maximum pause time was reduced by 38%. So we knocked a significant amount of time off our maximum pause time. The average went down 13%, and we spent 11% less time in GC. So all of those things improved our performance, and all I had to do was give my box or my partition an extra 1 or 2 gigabytes worth of RAM. Okay, so if we then go from the operating system and we start moving up to the runtime, really, for the Java runtime, it's all about garbage collection. Right? This is the only thing that you have much access to tune. There are hieroglyphic options available for adjusting the just-in-time compiler and this sort of thing. But in general, the only thing you should worry about making changes to is the garbage collector. And again, being able to do this is actually easy to diagnose and it's easy to change. You just add some command line options. So the amount of effort to change GC is just the amount of effort it takes to restart the system. So in terms of the Java runtime, memory is actually used for a fair number of things. When you start your process, memory is used for the OS and the C runtime. Right? The fact that you're running an operating system takes some memory. Your Java heap takes some memory, and the JVM itself takes some memory. And there is actually a relationship between the Java heap and the JVM's memory usage. So when you create a thread, right, a new Java lang thread object, that creates a thread object on the Java heap. But it also needs a thread at the OS level in order to be able to run what threads do. And it's the same thing for sockets. Anything that requires machine resource or OS resource has an allocation on the other side of the line. So you have both a Java heap and a native heap. And what you create on the Java heap may actually allocate memory in both places. So what memory problems are there? So the first of all, if you don't have enough Java heap or you don't have enough native heap, the other side, when you run out, you'll get an out-of-memory error. And that's going to give you a pretty bad performance problem because you basically shut down. And that's your worst performance, you're not running. So yeah, if you don't have enough Java heap or native heap, you'll have an out-of-memory error. What's actually worse than that Because if you have an out-of-memory error, you'll shut down and you can just restart the application. And for things like clusters, that's done for you automatically. What's actually worse is if you have only just enough memory in which to run. Because then you end up garbage collecting all the time. And you actually spend a lot of time in GC doing garbage collection rather than having an out-of-memory error and just restarting. So having only just enough memory to run is actually quite a bad situation to be for performance. So if you in that kind of situation, it increases your CPU usage for garbage collection because you're spending all of your time in GC. And so that's our performance problem, really, that you have to worry about. So in order to detect problems at the Java level, basically you want to get verbose GC output. That will tell you about the garbage collector. And if you care about native memory usage, there are tools you can use at the OS level. So PS, perfmon, svmon on AIX, and so on. Now, there are tools which will visualize both of these for you. In this day and age, you should not need to be reading verbose GC output. You should be loading it into a tool and showing it via graphing. It makes it significantly easier to work out what's going on. Now, there are various tools available which will graph verbose GC for you. One of them, I'll admit this is a plug from IBM, is called Garbage Collection Memory Visualizer. It's free, so there's no charge for it. You can download it. It's an Eclipse RCP-based application, and it will load in verbose GC output from Hotspot or from IBM. So that will give you graphing of memory usage, pause times, etc., as well as statistical analysis of everything that's going on. So it will tell you how much time you're spending in GC. It will tell you what your longest pause time is. And it will use that to try and highlight problems in your system. So if it thinks you don't have a large enough Java heap, it will tell you that. So, so GCMV will do this all for you, and it will also do it for the native memory, that non-Java heap memory. So you use OS tools to find out about that, whether it's PS or perfmon that we saw on Windows. And it gives you a script that you can run in order to gather the data, and then it will load it in, do the statistical analysis and the visualization for you. So again, that works on any operating system. So if we run our test, what we see here is that the Java heap usage, that blue line, is at about 100 meg. And the Java heap size is at 128 meg. So we're using the vast majority of our Java heap. We don't have a lot of spare space. So at this point, with this configuration, our proportion of time spent in garbage collection is listed as 8%. So we're spending 8% of our time doing garbage collection and 92% of our time running the application. So in general, that's a bad number. You should be able to get garbage collection overhead for almost every system down to 1 or 2%. But the thing to notice there is that the garbage collection overhead is currently 8%, and the target we can get to is 1 or 2%. So all the tuning that you would ever want to do to garbage collection is only going to get you 6 or 7% worth of throughput in this case. Right? If we took the GC overhead down to 0, I've only gained 7, 8% throughput. So tuning garbage collection, tuning the JVM is not a panacea for performance. You're not going to run 2-3 times faster by modifying the JVM. You're going to get maybe 5%. But in this case, we're using 100 megs worth of Java heap out of 128 meg. So we're using 80% of the heap at any given point in time. So the theory on garbage collection heap occupancy is that you want to keep heap occupancy roughly in the middle of Java heap usage. Because if the occupancy is really low, if the amount of memory that you're using is, say, only 10% of the Java heap, you actually spend longer doing garbage collection when you garbage collect because you're traversing a lot more memory than you really needed to. So you're also wasting memory there. And as we said, if that's RAM that something else can be using, then another process may be suffering from lack of RAM. So ideally, you don't want to have your occupancies actually being too low. But more critically, you don't want it being too high. If your occupancy is up at the top, so you're using, say, 90% of the Java heap, Because you're using 90%, you've only got 10% to allocate into before you have to do a GC cycle. And that means you can say allocate 10 megs worth of data, then garbage collect. Allocate another 10 meg, and then garbage collect. If you could allocate 100 meg before your next garbage collection, then garbage collection would be only 1 in 10. So a tenth of the frequency of garbage collection. So you want space at the top. And usually the guideline is to make sure your occupancy is somewhere between 40 and 70% of the total Java heap size. Anything above 70% really is too much. Anything below 40%, you could probably shrink the heap. And in fact, for the IBM garbage collector, that's the trigger points in which we expand or shrink the heap. Above 70% will expand, under 40% will shrink. But the guideline of keeping a window in the middle applies to Hotspot, JRocket, IBM, whichever you're using. So, resolving the problem. If your Java heap isn't big enough, well, change -XMX, make it bigger. Again, because we don't want to cause a paging problem, you need to make sure you've got enough RAM on your system to be able to do that. And you want to make sure that, as we showed back here, you've got a Java heap, and then you've got this native heap thing, which is what's used by the JVM. Now, the amount of memory that's used for the native heap is just what's left over once you've allocated the Java heap. So if you make the Java heap too big, you're actually constraining the native heap. So ideally, you do need to measure both and understand what the memory usage of both is before you start increasing the Java heap size. But in our case, our Java heap size is small, so it's not a problem. So we've gone from, we have our case where we're using about 90% of memory. And if I then increase the Java heap size, so I get it into this 40 to 70% window of occupancy, and I rerun my test with my increased Java heap size, I'm now still using 100 megabytes worth of live data, but my heap size is now more like 160 megs. So I'm in that 40 to 70% region. And my GC overhead, the amount of time spent running GC rather than running the application, has now dropped from 8% to 3.3%. And that means I've gained 4.5–5% of performance just by changing a command line option to give myself a little bit of extra Java heap. But at this point, my GC overhead's down to 3%. So any incremental improvement to GC tuning now can only gain me 3% of throughput. So the effect is to reduce overall time in GC by about 60%. However, that's only 4.8% of my application throughput. So far, paging got me about 4%. Changing GC has got me 4.8%. So I've improved my performance by 8.8%, which isn't a huge amount, but all I had to do for this was assign a bit more RAM and change a -XMX option on the command line. So it's pretty quick to do. And the effect that this has had on my performance benchmark, because I've now run it again to make sure this has actually made an improvement, is before I had this, I fixed paging and it got a little bit better. Now I've fixed garbage collection and it's got a little bit better again. So I've now got an improved picture. So there's the overall breakdown of improvements per page. In general, they're not great. One page is now 30% faster, but that's because that page didn't take long in the first place. Overall, I've got about a 4% incremental gain. So next, I've looked at the operating system. I've looked at the Java runtime. Next, I'm going to look at the application itself. So for the application, you care about memory, you care about CPU, you care about synchronization, and you care about I/O. So all of these are candidates for the application itself. In the case of memory, it's usually that I've allocated inefficient collections. I'm traversing down an array list rather than using a hash map, and that's causing me a problem. For CPU, it's often that you don't have enough threads, and therefore you don't scale as you add more CPU. And that's kind of the other side of synchronization, where you've got bottleneck locks inside your code. So the approach to looking at this is to first start by looking at CPU usage. So Effectively, this is just doing simple analysis of your code to find out where the CPU time is being spent and whether we can reduce the amount of CPU time that the code takes to perform the function that it does. So there's various ways of doing this. And the one that we use inside IBM is using a tool called Health Center. JRocket has mission control, and we'll go through looking at that in a second. The other thing to look at first is synchronization. So this is where you have locks, synchronized blocks of code, and you have multiple threads trying to access through that lock at the same time. Now, if you have lots of threads trying to access the same data structure, it's not necessarily a problem. Contention isn't a problem unless when that lock is taken, the thread that works on that data takes a long time doing it. So it's a mix of how long a lock is held for and how often it's contended. So those are the two interesting bits of data that we care about. So first of all, trying to identify where there's CPU and performance inefficiencies in your code. So this output here is from an IBM tool called Health Center, which is free. You plug it into the JVM, but it only works for the IBM platforms. And what it does is it gives you a breakdown of what methods are using how much of your application CPU. So in this case, it's identified a method that's in the shopping servlet that's using 80% of the CPU of the Java application. And at the bottom, it gives you a tree. And that tree is the method call graph. So what method is called what method, which is called what method to get me to my servlet method that's causing me a problem. As I said, this is IBM, but JRocket with mission control does the same thing, and there are third-party tools which will walk through and find CPU bottlenecks as well. So if I look at this, and I say, okay, so I'm spending all of my time in plants by WebSphere shopping servlet deliberate slow method. That might be a candidate for optimization. And in fact, in the case of Health Center, on the left-hand side, it does some analysis of the data it's got, and it says deliberate slow method might be a CPU hog that's appropriate for optimization. So if we look at the next bit, which is our synchronization, again, Health Center will look at every single lock that's running in the system, and Mission Control does the same thing for JRocket. So it analyzes every single synchronized block, whether it's JVM level or whether it's application level, so object locks, and it tries to work out whether or not there's any contention and how long those locks are held for. So we've got some high bars, and these are actually that the lock is contended. So in this case, 1% of the time, a thread that wants to get that synchronized block has to wait because someone else owns it. But the bar is green, and the reason the bar is green is because when a thread holds that lock, it holds it for a very, very short period of time. So yes, one time in 100 I'm going to have to wait, but I have to wait a couple of microseconds. So that really isn't a problem. What Health Center will do is it will paint bars red when they become a problem, so that you've actually got something to go and look at. So in this case, I've got an alert that says I've got a deliberate slow method, which is running slow, and that I don't have any problems with my locking. So if I look at the code for deliberate slow method, someone's written a loop that just waits for a time to pop and then stops going through the loop. So it's a banal test to show that this is what you need to look for. So if I fix that, what happens is this was my original baseline. And from my baseline, I went to fixed paging, and I got my 4%. I then fixed the fact that the Java heap wasn't big enough, and I made the Java heap bigger, and I got another 4.8%. So at this point, I've got an 8.8% performance improvement. And then I fixed some bad code. And suddenly, for the shopping servlet, I've got what looks like 10 times faster. And for this one, I've got significantly faster as well. So in two cases, doing some modification to the code has given me a huge increase. So in the case of one of them, I've got a 5x performance improvement, and in the case of the other one, I've got 20x. And an overall performance gain of 48%. Now, this is a fairly banal case. It is that I made some code spin for a little bit of time. So you're never going to find anything that should be quite that bad. But the important thing here is actually that you tune the operating system, you get single digits. You tune the JVM, you get single digits. And this is because smart people that work on operating systems have been doing so for years, and they've optimized out-of-the-box performance so that it is 95, 99% of the time right. And it's the same for the JVM. Huge amounts of work are done in the just-in-time compiler and in garbage collectors to make them self-tuning and so on. So there isn't much that you need to do, and even when it's wrong, it's not catastrophically wrong. Whereas, let's face it, most applications don't have a huge user base, and they don't have, Java's got 15 years, operating systems have got 30 years of pedigree. So that's where it's most likely that you're going to be able to get performance improvements. So I've identified a problem in my code and I fixed it, and I've got 48% overall and 20x for one of my servlets. So the next thing to do is then go back and check that this has actually fixed something. So at every stage, you need to go back and look and make sure you haven't broken something and look for the next improvement. And now looking at the CPU profile, it all looks pretty good. There's nothing that's actually using a huge amount of CPU. So that seems to be okay. And I can go back and look at the locking to see whether that's now become a bottleneck. And there's nothing obvious there either. So actually at this point, I've got a fairly well-running application, which you would hope, because it is a sample that we ship with the WebSphere. So we're trying to show it off as something that works well. So yeah, I mean, we've got a well-running application. And by the way, we don't ship it with deliberate slow method. I did that. So the summary is that when you do performance testing, you do need some key things to begin with. One is a repeatable benchmark. You need to run that benchmark, make a single change, run it again, and make sure that you're always getting better. And in fact, you don't want to run it just once. Right? You do get those variations. So when you run a benchmark, you could actually do with running it 5, 10, 20 times after you make a change to make sure that you've got a full set of measurements and they correlate with each other and you don't have a one-off anomaly. So you need to do that. In fact, performance is something you should ideally be doing constantly. And if possible, measure this stuff in production as well. In terms of being able to find out what's going on, you don't need to be going into log files anymore. There's visualization for all of this. So Windows is particularly good that it will graph perfmon for you. Perfmon's a visual tool. For most of the OS logs that you can use to look at memory and CPU and so on, there are visualizers for it out there. We provide one called GCMV that is free, and it works for verbose GC, and it works for some of the OS stuff. And then when it comes to your application, there are, again, free tools out there. So Mission Control's free in development. Health Center from IBM is free in every case, so production is free as well. And this will visualize the data for you and try to identify bottlenecks and do statistical analysis. Right? Performance is something we're trying to make easy for everyone to do. And most importantly, don't think that there's a go faster button on the JVM or in the operating system that we don't tell you about because we want to sell you services. Right? It's not there. The only thing you can do is usually play around with GC a bit. But remember, if you start off with a GC overhead of 8%, you can only save 8%. So usually it's not the problem. The problem's going to be somewhere further up the stack, whether it's actually middleware code, whether it's your application code, whether it's third-party code. In a lot of ways, you should just look at whose code's newest, because they're probably at fault. So, in summary, yes, infrastructure affects performance. Yes, garbage collection affects performance, but yeah. The application's most likely where it is, but I would always start your analysis at the bottom. And that's because it's easy to look at and it's easy to correct. Whereas if you've got fundamental problems in the application, you suddenly have to start grabbing large numbers of developers and discussing whether or not you actually need to change your architecture. And that's something that introduces risk into the project and takes a while to be able to design and implement and deliver properly. So there's a whole bunch of references, and as I said, the slides are going to be on SlideShare, so you can download them from there, and they should be there by Monday. Okay, any questions?